Hello. So, I'm back. We have 2 weeks of actual instruction left. I can't believe it. We're almost done. Sort of ready for it. You probably are as well. It's really weird, believe me, the challenges of doing this, teaching, or from your point of view as a student, I'm sure it's been very challenging. So, well, we're almost there. So we've got 2 weeks left, and in that time, I'm just going to do some inductive logic, and we're just going to look at 2 things. Normally, we'd look at more things, but we just don't have time for it, and I don't want to overwhelm you because everything is already overwhelming. So we're just going to look at 2 things, okay? We're going to look at enumerative reasoning, which has to do with statistics. I'm not going to make you do a bunch of math. It's just going to be understanding how polling works and how statistics works in general, okay? But it won't involve any actual math. And then I'll look at scientific reasoning and some of the things that go into making a good scientific theory. And these are actually very much applicable to everyday life, to your everyday thinking. So that's going to be interesting, okay? So those are the 2 things, and then we'll review for the final, okay? So you are definitely getting a slightly skinnier version of this course, right? We just cannot get into as much detail, and I feel bad about that, but that's just how it is. We're still going to get through everything. We're still going to cover all the basics that you ought to cover in a class like this. Okay? With that said, let us proceed. Let's see. Okay, so just a little reminder, deductive versus inductive, right? We've been doing deductive. You did propositional logic and then categorical logic, right? So in a deductive argument, if it's a good one, if it's a valid deductive argument, then the conclusion must be true if the premises are true. We saw this in propositional logic, and then we saw it in categorical logic as well. And in categorical logic, it was very obvious that the conclusion has to be true because you just see that it's there. Once you've plugged in the premises, you see the conclusion just show up, right? And so then you know that it's valid. Some examples right here is a categorical logic example. All cats are mammals. All mammals are animals. Therefore, all cats are animals. You realize this, right? Of course, if this sentence is true and this sentence is true, then this sentence has to be true. And if you were to make a Venn diagram for these 2 premises, then you would see this this premise right here show up. Or if you were to put it into propositional logic language, use P's and Q's or whatever you want, and use the logical operators, you would be able to show using the shortcut method that this argument is valid. Of course, you'd have to translate it into propositional logic, but here's something that's easy for propositional logic to handle, right? If we have free will, then not everything is determined. Everything is determined, so we don't have free will. So this is another valid argument. If these premises are true, then the conclusion must be true. Of course, if you don't think the conclusion is true, then it's probably because one of the premises is not true, right? And both of these premises are questionable. If you take an intro to philosophy class, you talk about both of these premises, and they're both questionable. Lots of people question both of these premises, but the validity is not in question. If these premises were true, the conclusion would have to be true. Anything numerically identical, x has property p. Y is numerically identical with x, so y has property p. Another deductive argument that's valid, where the conclusion follows logically from the premises. Okay. In an inductive argument, if it's a good one, and for good inductive arguments we use the word strong, then the premises support the conclusion by showing that it's very likely to be true, right? Not necessarily. So this is why you can't really do inductive arguments in the same way as propositional arguments or categorical arguments, because with those, the conclusion must logically necessarily follow. It must be true if the premises are true. Inductive arguments, that's not the case, right? In a good inductive argument, if the premises are true, the conclusion is very likely to be true, but it could be false. It's logically possible. So the truth of the conclusion is not guaranteed by the truth of the premises. It's just very, very likely. Okay, and sometimes it's so likely that it's as good as certain. If you take your own sensory experience as an example, right? You look around the room, you see what things look like, and you can conclude that you are really in a room. Right? You're gonna not think that you're in a dream or in a Matrix type situation, but hey, it's logically possible. It's consistent with your sense data, right? So the mere fact that you're looking around the room and it looks like you're in a room, well, that provides very strong support for the idea that you really are. But it's logically consistent to suppose that you're having these experiences even though you're dreaming. Right? It's possible, but it's so unlikely that we don't even treat it as something probable. We treat it as certain. But it's good to recognize that it's not actually completely certain. Right? It's possible that you're wrong, even though you've got true premises. Okay, here's an example. A less weird example than might I be dreaming. Right? The service at Arby's is always bad. Every time I go there, the waiters are rude and unprofessional. You see that? So here's a conclusion. The service at Arby's is bad. What are you basing that on? Why do you think that's true? Well, every time I go there, I have this experience of the waiters not being professional and being rude and things like that. Right? So I'm basing my conclusion on my experience. Of course, here I'm making a very bold claim. I'm saying it's always bad, right? I'm basing that on my own limited experience. How many times have I actually gone there? That's an important question to ask as well. Right? So, yes, this statement is supported by the second statement, right? This conclusion has some support, but it's not clear how strong it is. And it's certainly obvious that even if this is true, even if I've always had a bad experience, it doesn't necessarily mean the service is always bad. Here's another kind of inductive argument. Chimpanzees are very similar to humans biologically. If a certain drug, when given to a chimpanzee with a particular type of cancer, makes the chimp better, then it will probably do the same for humans with the same type of cancer. And this is the reasoning behind a lot of research where people test on animals, right? Not talking about the ethics of that at all. It's just simply a fact that researchers use animals as stand-ins for human beings, because a lot of our biology is very similar to other animals. So even rats get tested and tested on and experimented with in the hopes that it'll tell us something about human beings. Right? So this is a kind of an argument from analogy. So, well, these animals are similar enough to us so that it's at least probable, or it's more probable, that a cure for them will also be a cure for us. Not necessarily the case, though. See, it's inductive. You might get lucky, but it might not be true. The conclusion may end up being false, right? That perhaps there's some reason that the cancer treatment works for the chimp, but not for a human being. It's possible. Whenever I heat water in a pan, the water eventually boils. And then I draw a conclusion. And I think, okay, well, if that's always happened in the past, then if I heat water in a pan now, it'll boil eventually. We learn lots of stuff like this. And this is, it's strange to think that perhaps it's possible that it won't boil, but you have to think about this in terms of logical possibility, right? So this is a very strong argument for the idea that water is going to boil every time I apply heat. Right? We're not going to think any differently, but as the philosopher David Hume pointed out a long time ago, it's not logically inconsistent. Right? You could imagine tomorrow trying to turn on the water, and there's a flame underneath the pot, but it somehow just does not start boiling. Completely unlikely. That'd be miraculous, right? But it's logically possible. It's consistent with the evidence so far, right? Even though this always happened in the past, we don't know for certain that the future will resemble the past. Why don't we know for certain? Well, we haven't experienced the future yet, right? Okay, so those are all examples of inductive arguments, some better than others, but the main takeaway point here is that with a strong inductive argument, all you get is very strong support for a conclusion. The conclusion is not logically entailed by the truth of the premises. So there's at least three different ways of dividing up different types of inductive reasoning or different types of inductive arguments. We're not going to do all of these. We're going to look at the most important one for our purposes, enumerative induction. Causal arguments will be touched on by the scientific reasoning part of the course anyway. Okay, analogical deduction is very tricky. It often does not work. I'm going to focus on enumerative induction. That has to do with polling and statistics and things like that. And that actually has quite a bit of relevance today to coronavirus testing, right? There's some interesting things there to understand about that. Okay, so inductive reasoning, three different types, yes, but we're only going to look at this one. So don't freak out, then don't get too overwhelmed. Right? So this is all we're doing today, is looking at the basics of enumerative induction. It's where you reason from premises about individual members of a group to a conclusion about the group as a whole. Okay, give you an example, right? This example that I already gave you, that's like that. Right? I'm saying that the service at Arby's is always bad. I'm saying a general thing about service at Arby's, but I'm basing that on particular examples of service at Arby's, right? The examples that I've encountered. So if we think of the group as being service at Arby's, then the individual members as well, the service that I had on those particular days that I went there. Right? So I'm saying, well, I've had these particular bad experiences, and now I'm going to generalize to the whole entire group, right? This time I'm saying all service at Arby's is bad, but I'm basing that on, I haven't experienced all their service throughout all their years, right? I'm basing this here just on my experience, which is limited. So I'm generalizing on the basis of particular experiences in that case. Okay. Analogical induction, again, we're not going to get into detail. I just quickly am going to say what it is, okay? But you don't need to learn about it. I just want to bring it up. It's when you infer that since two or more things are similar in certain ways, they must be or might be or probably are similar in other ways. Right, so this is the example that I had up earlier. Where, chimps are very much like us biologically. A lot of similarities. And so if they can get diseases like human beings, and then if a treatment works on the chimpanzees, there's a high probability that it's going to work on humans as well. But all it is a high probability, right? Not absolutely certain. Okay? And then causal arguments. It's an inductive argument whose premises support a causal claim about one thing causing another, like this, for example. Right? I've had these particular experiences in the past of whenever I heat water in a pan, it boils. And then I draw a conclusion from that. I come up with some sort of causal knowledge, right? Now I know that, okay, if I want water to boil, I'll introduce some heat to it. But again, it's logically possible that it won't boil, even though we don't think it's physically possible. It has nothing to do with that. It just has to do with the logic of it, right? It's just the difference between deductive and inductive. With deductive, it would be even logically impossible for the conclusion to be false. In this case, the conclusion could be false, logically speaking, not physically. Okay, if these are not clear to you, that's not a big deal, right? Like I said, we're going to focus just on enumerative induction. Okay. So like I said, it's where you reason from premises about individual members of a group to a conclusion about the group as a whole. A different way of saying it is you're making a general inference on the basis of particulars. So examples, this one again. Here's a classic example. All the crows that I've seen have been black. And suppose I am an ornithologist or something, someone who studies birds, and I've gone all over the world, and I've discovered all these crow populations, and they're always black. At a certain point, you might feel justified in saying, okay, crows are black, right? But of course, you have to keep probably in there, because is it possible that we might find a crow that isn't black? Well, yeah, of course it's possible, right? So we can make these generalizing statements, but they're always going to be probable, because it's possible that we have not experienced the entire group, right? That's the whole thing, is I'm basing a conclusion about the entire group of crows just on the experiences that I've had with particular crows. Again, going from the particular to the general. Oop. Or this one. Let's say 70%, 75%. Oh, that's a little weird. Ignore this CR right here. I don't know why I have two CRs in there. 75% of CR students that I've talked to have brown hair, right? So let's say I've done an informal poll, and every time I talk to CR students, I note down their hair color. It'd be very strange, but and I see that roughly 3/4, 75% of them have brown hair. Now I'm basing that just on the people that I've talked to, but then I might generalize and say, okay, well, that's probably representative of the overall CR student population, right? Now, of course, this is going to depend on how many people I talk to, right? And that's something that we'll get into in just a second. But some of you may already be thinking about that, right? So if I finally talk to 4 people, I should not be so confident about my conclusion. I don't know why it keeps showing this. It's rather annoying. Okay. No. Whereas if I talk to, dozens and dozens and dozens, and about 3/4 have brown hair, then I can conclude that's probably representative of the overall student population. Probably roughly 3/4 of the CR students have brown hair. Then I'd have a lot more confidence in my conclusion. It would be a stronger inductive argument. Right, so to talk about those types of arguments, there's just 3 vocabulary items that you should learn about. And this sounds all complicated at first, as a lot of times this stuff does, but then once you get it, it's actually not all that complicated. Okay, so let's use this enumerative induction argument as an example. Say 40% of Americans polled believe that the Earth is less than 10,000 years old. So, approximately 40% of Americans believe that the Earth is less than 10,000 years old. Right? Every now and then you'll see polls like this crop up, and where we talk about people's beliefs about the nature of the universe. And indeed, it is a quite high percentage of people tend to report that they think that the Earth is less than 10,000 years old. This is usually because they're basing their understanding on religious ideas rather than scientific ideas. And we're not saying anything one way or the other about that. Here, what's important is the polling that's happening, right? Okay, so keep this in mind here, right? So people get polled, people get asked what they think about a certain issue, and then you get the results. So 40% of the Americans that were polled believe this. And then the conclusion is, so probably around 40% of Americans in general, including the ones that weren't polled, believe that the Earth is less than 10,000 years old. Right? All poll results like this are based on a limited sample. It's never the case that all Americans are interviewed or polled for a certain issue. It's always going to be a smaller sample. So the target group, right? A target group, that's the group as a whole, the whole group that we're talking about. And here, right, the conclusion is talking about Americans in general. Not just the Americans who are polled, but Americans in general. That's who we want to know something about, right? What percentage of Americans believes in a young Earth, right? Sometimes it's called young Earth theory, or young Earth creationism. What percentage of Americans believes that? So we're curious about Americans, but to get this figure right here, we're basing that on the Americans who were polled, the people who actually filled out a survey. Right? So that's the sample members. Right? That's the Americans who participated in the poll or the survey. They're the sample members, right? We're not looking at the entire group. We're just looking at a sample. And the same way that you might, you have to figure out the pH balance in your swimming pool. You don't need to check every part of the pool. You just check one part of the pool. Right? So the same thing here. If you can get a good sample going, then we can be relatively confident that our conclusion is about right. And the relevant property is the thing that we're interested in, right? So the target group is Americans, and what do we want to know? Well, how many of them, what percentage believes that the Earth is less than 10,000 years old? Right, so that's the relevant property. So see, the vocabulary, it's not that difficult, really. Target group, what's the group that you're talking about? Or the relevant property is, well, what do you want to know about that group? And then the sample members is, those are the ones that you actually investigate. Right? Those are the ones that you actually poll or survey. Or if we go back to the crows example, right? The target group there would be all crows in the world. The sample members would be all the crows that I've actually investigated in all my bird studies. And the relevant property is what color they are. Right? Pretty simple. Okay, so then sample size obviously is very, very important to that, right? How many sample members are you actually checking on, whether interviewing or observing, surveying, whatever it may be, versus how many target group members there are? So let's say, for example, there's 3 million ambidextrous people in the U.S. And ambidextrous meaning you can write with your left and right hand. That's all that means. And you want to know how ambidexterity correlates with political alignment, right? It's an interesting question. We might not find out anything interesting, but it'd be weird to find out, for example, that ambidextrous people are more likely to be liberal or more likely to be conservative or something like that, So you might want to find out about that. So if there's 3 million ambidextrous people in the United States, and you want to know if there's any sort of link between being able to write or use both hands equally and then your political alignment, that's an interesting question. You might want to find out about it. You're not going to interview all 3 million ambidextrous people, right? You're going to find a sample. Okay, so look at 2 different ways of doing this. You go per state. Right, you interview one ambidextrous person per state. So your sample size here is 50 people total. Or you interview 10 ambidextrous people per state. 500. Your sample size is much larger. Which one do you think is going to be more reliable? Well, hopefully everyone sees that the more people you interview, the more people you poll, the higher your accuracy is going to be. The more likely it is that this will actually represent the target group, right? All these 3 million people, right? Because you're trying to find out on the basis of a few people what's likely to be true about the whole group in its entirety. If you only have 50 people, that's just not a very big sample size, so it's not as likely to be reliable. Obviously, the second one, right? The bigger the sample size, the better. So that's always going to be the case here for enumerative induction, this kind of statistical argument. You want to make sure that your sample size is big enough, right? It's a large sample size. So anything with a very small sample size, especially when you compare it to the target group, right, which is here, 3 million, that's a lot. You're probably going to want it to be much bigger than just 50 people. And this is one of these things that gets overlooked when you look at surveys and studies, when you look at percentages. They're not all done that well, right? Anyone can do these kinds of studies and publish them, depending on where they're publishing them, but all sorts of stuff gets published online. You want to know, is the sample size really representative? Does it really give us enough of the target group for us to be able to draw a solid conclusion. Is there enough of the sample group to allow us to draw a solid conclusion about the target group? So if your sample size is too small and you draw a conclusion, that's actually a fallacy called hasty generalization. Right? So, for example, let's say you meet a Scientologist and she's very talkative. So you conclude that Scientologists in general are very extroverted and chatty. Right? So there's the target group is all Scientologists. Your sample group is the one Scientologist you met. The relevant property is being talkative. You end up concluding that all scientists are. Well, you clearly this sample group is way too small. You can't make that conclusion on the basis of just meeting one. Or let's say you find out how many CR students vote Democrat. Out of the 5 people that you asked, say you only asked 5 people, 2 tell you that they vote Democrat. And so then you conclude, well, most CR students, I guess, don't vote Democrat. I hope here that you would see that this is a problem. Right? There are hundreds of people at CR. You only talk to 5 of them. There's much more room for error there, right? Maybe you interviewed the first group of people who are hanging out together, and maybe they're all friends and they're all politically kind of coming from the same place. So maybe they're all Republicans. You just happen to bump into a group of friends who are all Republicans, and so, or maybe 2 of them aren't. But these are the sort of things that you have to watch out about. When you have a very small sample size, it's way easier to get insufficient data to really support your conclusion. Okay. Or here, go back to the Arby's example. I went there just twice, and it was bad both times. Sure, true premise, but my conclusion is that service at Arby's is always terrible. Well, clearly my sample size is way too small. Right. So this is something to keep in mind. Keep in mind sample size when you're looking at any kind of poll or any kind of generalization. Right? What is this data based on? Is it based on a very small sample size? Then it's not going to be as reliable as something that's much larger. There's this as well. The less homogeneous a group is in traits relevant to the property in question, the bigger the sample size should be. Let me explain what I mean by that. Let's say you want to find out how many teeth the average cat has, versus you want to find out how many toys the average child has. These are pretty similar. We're asking how many of a certain thing the target group has, but these are very different because there's much more variability in terms of how many toys kids have. Some kids have maybe 3 or 4 toys. Lots of kids have like 50 toys, or way different. You're not going to find as much variability when it comes to how many teeth a cat has. Maybe every now and then you'll find a cat with way less teeth. You're probably not going to find cats with way more teeth. They're probably going to have about the same amount in each case. So this is what we mean here. If there's a lot of variability, then you're going to want that sample size to be much larger. So this one you need to have a larger group, because here you're likely to get something that's representative even if you only get a relatively small sample size, because there just isn't that much variability in the amount of teeth that a cat has. But there's a lot of variability in terms of how many toys the average child has, so you want this sample size to be way bigger. Okay? Okay. A little glitch there. Okay, so sample size is definitely important, right? So generally speaking, larger sample size is always better. And then when you have a lot of variability, you really want it to be much larger. Representativeness is very important in this way, right? The sample should be representative of the target group. So, for example, let's say you want to find out about job satisfaction levels in the U.S. and you're going to poll some people, right? You're going to have this is your target group, is people who work, and what their job satisfaction level is the relevant property, right? So you're going to poll a bunch of people and ask about their experiences. Who are you going to poll? Who are you going to ask about their experiences? Well, if you just position yourself outside of a factory or something like that, I don't know how many, I guess we still have factories, right? I just imagined in my head an old-fashioned factory. Anyway, if you set up your survey outside let's just say a factory, and just ask those people who are working very, very difficult, hard labor jobs that don't make a lot of money. If that's your targets, if that's your sample, you're going to get skewed results, right? You should, if the target group is all workers in the U.S., all people with jobs, then you should pull people in different economic brackets and in different fields of work, or you're not going to get an accurate representation of how satisfied United States workers are with their job. I hope that's clear to everyone, because it's very, very possible that these people will not be as satisfied as someone who, say, makes a little bit more money, or maybe the work isn't quite as hard. Those people are more likely to be happy. So if you want an accurate representation of how satisfied people are with their job in the United States, you don't want to poll just a group who is less likely to be as happy. I hope that's clear to everyone, right? The sample should be representative of the target group. It shouldn't skew the results in the way that this might. So always be aware of who's actually being asked, who's actually completing these surveys and participating in these polls. Are they representative of the group that we're interested in? Or here, if you want to find out, go back to this young Earth creationism idea that the Earth is less than 10,000 years old, right? So we want to know what percentage of the U.S. population believes this. Well, you can't just go to a poll, go to a church and poll evangelical Christians, right? Because you're going to get a much higher percentage than what's actually accurate, right? Because evangelical Christians are much more likely to believe this. Right? So you could say, you could do this, you could interview just a bunch of fundamentalists and then say, look, 95% of the US believes that the Earth is less than 10,000 years old because 95% of my sample group believes this. Right? So you'd have an inductive argument, you'd have this enumerative induction argument, but the conclusion is not strongly supported at all. The conclusion is very unlikely to be correct because you're just not interviewing a group that's representative of the entire U.S. population, right? It is not as though most Americans are fundamentalist evangelical Christians. So it would just not be representative. You'd have to interview people from different walks of life, not just evangelical Christians, but all sorts of people. Then you would get a more accurate picture of how many people, what percentage actually believes this. Yeah. Or let's say you want to figure out what percentage of the population is depressed. Well, how are you going to find people to participate in your study? Well, it'd be very easy to just find some psychiatrists, right, and either get them to administer the poll, or maybe just wait outside wherever the psychiatrist works, right? However you do it, if you end up just polling those people who regularly visit a psychiatrist, you're sort of self-selecting, right? It's well, not self-selecting, but you're selecting a group who is more likely to be depressed because they're already visiting a psychiatrist. Not to say that everyone who visits a psychiatrist is depressed, but it's more likely that you're going to get depressed people, or at least there's a stronger possibility of that. So that's not going to be as representative either. Yeah. So if it's not sufficiently representative, you can call it a biased sample. You're biasing a certain group, a certain percentage of the population. And when that happens, even though you've got an argument, it's just not strong enough to say, okay, well, I can trust the conclusion. Again, even in a very strong argument, it's always going to be logically possible that the conclusion is false. But if you have something like, well, it's 95% likely to be true, then you can accept the conclusion, right, as being probably true. The same way that you accept that you are probably really in your room right now and you're not having a dream. So this can actually happen not just in this sort of scientific context of taking polls and surveys, but in everyday life. We have this thing called confirmation bias. So if you already think you know the truth about a target group, then we tend to just pay attention to the members of that group that confirm that belief, and you ignore members that could disconfirm that belief. That's confirmation bias. So rather than just targeting specific groups within the population, you should just make it random, right? Random sampling yields a greater representativeness. We get a more accurate picture of what the general population is actually like. So testing for the coronavirus is a really good example. Right now we're getting these percentages in terms of how much of the population is contracting this, and it seems to be very, very large. Of course, the people that are being sampled are people who already have symptoms of some sort, right? Testing has not been random most of the time. It's usually limited because, well, resources are limited, and the point here of the testing is to find out which individuals have it so they can be contained and so we can stop the spread and things like that. They're not necessarily tracking real life percentages in terms of out of the general population how many people have this. It is rather the target group is all people who already have symptoms, right? So it is much more likely that out of that target group there's going to be a lot more people that actually have COVID, simply because we already know that they're sick, because those are the people that are being tested. Right? So the results are going to be a bit skewed in that sense. Now, I'm not downplaying anything, right? It's just you'll find this acknowledged in most of the scientific literature on this. Most articles will acknowledge this as well. I'm just trying to relate what we're talking about here to something that's actually happening in our everyday life. Right, so when they say something like, whatever percentage it might be, they're basing this on a rather limited sample, and it's not a random sample. It's a sample of people who are already sick. So of course, the rates of people who contracted coronavirus is going to look much higher if you're only looking at that group rather than a random group. So the analogy here is, if you want to find out what percentage of the population suffers from depression, then you should poll random people of the population rather than just one specific group. Again, you want to know generally what percentage of United States population has depression. Don't just poll the people who are seeing a psychiatrist, because it's much more likely that they will have depression. In the same way, if you really want to know what percentage of, say, the United States has contracted coronavirus, if you really want to know it, you should have a larger sample than just the people who are already sick, because this is directly analogous to what is happening here. Okay. Another problem with representativeness is self-selecting. Right? Self-selecting samples are participants in studies who weren't randomly selected, as they would be ideally, but who chose to take the survey or the poll on their own initiative. So people who see a poll and they're interested in this, they may have a strong opinion on the topic that can skew the results, right? So it's not truly random if you're allowing people to make the choice in that sense, right? Here, do you want to take the survey? People who very much want to, that might skew the result. They might not be entirely representative of the entire population. So that's another problem. So again, random sampling gets rid of a lot of these defeaters for strong enumerative arguments. Okay, so quickly look. Right, so sample size and representativeness are really, really important here. So when you look at any kind of study that's been done that tries to show some sort of general result based on particular cases, keep those things in mind. How big is the sample size and how representative is the sample size? Okay, we're almost done here. Here's something that you're not going to really have to worry about, but it's just part of these kinds of arguments. Right, so as we said before, any kind of enumerative argument, because it's inductive, even if it's a very strong argument, the conclusion is not 100% guaranteed, right? Because it's not a deductive argument. So margins of errors come in there, right? Now, those are calculated with statistics, and we're not going to do that, right? It's not a statistics class. This is more to make you aware of how this works, okay? So margins of error, a margin of error tells us how far off, in terms of percentages, the predictor percentage based on the sample group is from the actual percentage based on the target group. So this is usually built into the surveys, right? If you have a conclusion that says, let's say 75% of CR students have brown hair, and it says that the margin of error is plus minus 5, okay? You can translate it in your mind then as saying, all we really know is that the actual percentage is somewhere between 70% and 80%, right? 75 is right in the middle of those two. There's a 5-point error margin on either side. So when you see something like 75% with a margin error of 5, translate it in your head as, well, subtract 5 and add 5, and that gives you the range, right? The actual percentage is somewhere between 70 and 80. That's very important because you could have a margin of error that's very large, right? You could say, what if it said 60% of CR students have brown hair? Well, then you would conclude most CR students have brown hair. But what if the margin of error for that was 10? Then it's possible that actually only 50%, in which case only half of them have brown hair. Right? So it's important to keep errors, margin of errors in mind. Okay. I think I just had a stroke. A margin of error. It's not that hard to say. Confidence level is related to this. Okay. And that's the probability that the sample group will actually accurately represent the target group within that margin of error, right? So you have the margin of error, but then you also have your confidence level that the relevant property will actually be in that range somewhere. And so it's just a way of mathematically modeling the probability of error. And again, to do this properly, you have to get into statistics. We don't need to do that. You just need to be aware of the way that it works. So if we assign a confidence level of 95% to the results of a poll, that means that there's about a 5% chance that a sampling error was made. And there's always going to be a chance of sampling error. That needs to be included in our model. Because there's always a possibility of error, and we need to include that. Okay. So yeah, we're not going to do an analogical induction, so we can actually stop right here. Okay, so just quick review. You know, enumerative arguments, you're looking at a particular sample to find out about the whole group. The whole group that you're trying to find out about is the target group. The sample members are the ones that you're studying or polling or surveying, and the relevant property is the thing that you're asking about. In order for you to have a strong enumerative argument, you're going to want to make sure that your sample size is large enough, and you're going to want to make sure that your samples are representative, so that they're likely to represent the group as a whole and not just some particular subsection of the population. Okay. And then statistics-wise, just be aware of this, that there's always going to be a margin of error, and there's going to be a confidence level percentage associated as well. Okay, that's it for now. I will see you soon. When next video I make will be on scientific reasoning. Okay, bye.